What's the trick to factorize x to the 4 plus y to the 4 plus x squared y squared? One of the most useful identities in competition maths is the sum of squares. X squared plus y squared equals x plus y squared minus 2xy. The trick here is noticing that our equation almost fits this pattern. X to the 4 plus y to the 4 equals x plus y to the 4 minus 2x squared y squared. If we add the x squared y squared to both sides, we get x to the 4 plus y to the 4 equals x squared plus y squared all squared minus 2x squared y squared. So just comparing these two, the only thing that's changed here is that we've replaced the x with x squared and the y with y squared. Everything else in these two equations is the same. So now comparing this with our original, we know that we need to add an x squared y squared to both sides. So x to the 4 plus y to the 4 plus x squared y squared equals x squared plus y squared all squared minus 1 lot of x squared y squared. So this step is the key insight. We're forcing this perfect square and this sum of squares identity onto our original equation, and then we're adjusting it. But we haven't factorized it yet because we've still got this minus sign here. We've got a second trick to combine these two terms. Both of these terms are squares and we are subtracting them. So we can factorize this using the difference of two squares. The difference between our formula and our example is our a is x squared plus y squared and our b is xy. So both of these terms are squares and we are subtracting them. So we can factor this like using this formula: x squared plus y squared plus xy times x squared plus y squared minus xy. So that's your full factorization. And when students learn these common factorizations like the difference of two squares and like the sum of squares or a perfect square, they can apply them to many unusual situations like this. And this unlocks a whole new level of algebraic thinking. And that's exactly what competition maths develops.